Far beyond the familiar gas giants of our solar system like Jupiter and Saturn lies the Kuiper Belt, a vast frozen graveyard of solar system leftovers, a region teeming with icy objects and remnants from the early days of our planetary neighborhood. Pluto, once dismissed as a static, icy relic, a lonely sentinel at the edge of our solar system, was long thought to be geologically dead and unchanging, a frozen world devoid of any internal activity. Its thin atmosphere, mostly nitrogen, a wispy veil clinging to the surface with traces of methane and carbon monoxide, seemed fragile and fleeting. It was widely expected to freeze and collapse entirely, solidifying onto the surface as the dwarf planet journeyed further from the sun, as Pluto drifted away from the sun in its elongated, eccentric orbit. For years, Pluto was a cosmic afterthought, relegated to the fringes of our understanding. Remote, enigmatic and presumed inert, a celestial body of little apparent interest. But in 2015, NASA's New Horizons spacecraft, after a journey of nearly a decade, changed everything, rewriting our understanding of this distant world. The images revealed a world of heart-shaped plains now known as Tombaugh Regio, towering water ice mountains, rising thousands of meters above the icy landscape, and deep chasms, evidence of immense geological forces at play. The surface showed undeniable evidence of recent geological activity, defying all expectations. Pluto was no longer a dead world, a frozen ball of ice and rock, but a dynamic, complex planet, a world of surprising geological diversity, with a surprisingly substantial, multi-layered atmosphere extending far into space, tinged with a delicate blue haze, hinting at complex atmospheric processes. The flyby shattered our assumptions about small, icy worlds in the outer solar system, and left us with new mysteries, questions that continue to drive planetary science today. How could such a small, cold world so far from the sun's warmth maintain such complexity and activity on its surface and in its atmosphere? Pluto, once a planetary footnote, a distant and seemingly insignificant object, became a scientific headliner, a source of fascination and intense study, challenging our understanding of what a planet can be and forcing us to reconsider the very definition of planethood. The New Horizons mission, a triumph of engineering and scientific dedication, set the stage for an even deeper investigation into the mysteries of the Kuiper Belt and the fascinating world of Pluto. Pluto was not the simple frozen relic we expected, it was something far more intriguing. It was a vibrant, active world, a testament to the power of geological processes even in the coldest reaches of our solar system. That defied classification, a unique and extraordinary world that continues to surprise and inspire us. In science, the greatest discoveries often come from confronting the unknown. As astronomers prepared to aim the James Webb Space Telescope at Pluto, they felt a mix of excitement and apprehension. New Horizons had revealed a complex atmosphere, but its mechanics remained a mystery. Theories based on Earth, Mars, and Titan fell short. What if Pluto's climate followed rules we'd never seen? A radical hypothesis emerged. Pluto's haze, made of organic tholins, might be cooling its atmosphere, not warming it. If true, this would overturn our understanding of planetary climates. JWST's observations could confirm this anti-greenhouse effect, but doing so would force scientists to rethink everything they knew about atmospheric physics. The stakes were high. Pluto's strangeness could be a clue to a much larger, more complex cosmic reality. The fear wasn't just that Pluto was different, but that its difference was a window into the unknown. What if other worlds operated by these unfamiliar rules? Enter the James Webb Space Telescope, designed to see the universe in infrared, the light of heat. For Pluto, this meant more than just a picture. It was a planetary diagnostic. JWST's challenge: separate Pluto's faint atmospheric glow from the light of its moon, Charon. Only Webb's precision could isolate Pluto's thermal fingerprint. The data was spectacular. JWS detected methane's thermal signature and found Pluto's atmosphere was far colder than expected. The culprit, the haze, acting as a planetary coolant. Sunlight breaks down methane, forming haze particles that absorb energy and radiate it away as infrared light. This process actively cools Pluto's atmosphere, creating a climate system unlike any other in the solar system. JWS didn't just observe Pluto, it uncovered a new kind of climate. The discovery rippled through planetary science, forcing a rewrite of the rules. Pluto's haze was no longer a curiosity, it was the engine of a revolutionary climate. The James Webb Space Telescope has opened our eyes to aspects of the universe we could only dream of before. Its observations are constantly challenging our understanding of celestial bodies. JWST's findings forced us to confront a paradox. Pluto's atmosphere, in a surprising twist, cools itself, exhibiting behavior that is the complete opposite of what we typically observe on planets like Earth or even Titan. On most planets with substantial atmospheres, certain atmospheric particles trap heat radiating from the surface, creating a greenhouse effect that warms the planet. But Pluto's haze, defying expectations, does the reverse. It acts as a master cooler, a natural refrigeration system for the dwarf planet. High in Pluto's tenuous atmosphere, sunlight interacts with methane molecules, breaking them down into more complex hydrocarbons, initiating a cascade of atmospheric chemistry. These hydrocarbons then condense and aggregate, forming fine haze particles suspended in the upper atmosphere. These tiny particles then absorb incoming solar energy, and instead of trapping the heat, they radiate it away as infrared light, effectively bleeding heat into the vastness of space. The result, a net cooling effect so powerful that it completely overwhelms any potential greenhouse warming that might otherwise occur. In essence, Pluto's atmosphere is constantly refrigerated by its unique haze layer, creating a real-world example of an anti-greenhouse effect in action. This remarkable discovery fundamentally upends our existing models of planetary climates and atmospheric behavior. It vividly demonstrates that context, the specific atmospheric chemistry, the prevailing pressure conditions, and the sheer distance from the life-giving energy of the sun, can combine to create planetary climates that utterly defy our preconceived notions and intuition. Pluto isn't simply an oddball, a cosmic outlier. It serves as a profound lesson in cosmic humility, reminding us of the limits of our current understanding. The universe, in its vastness, is far more creative and complex than we could have ever imagined, and our current assumptions about the behavior of planetary atmospheres are undoubtedly incomplete. Pluto's climate stands as a profound and humbling reminder that the cosmos is full of mysteries and always has astonishing surprises in store for those who dare to explore it. Let's dive into the fascinating workings of Pluto's climate engine. It's a world where familiar processes take on strange and unexpected roles. Sunlight, the primary energy source, initiates a cascade of chemical reactions. It relentlessly breaks down nitrogen and methane molecules in Pluto's upper atmosphere, creating complex hydrocarbons and tholins, those reddish-brown haze particles that give Pluto its distinctive color. These particles are essentially complex organic molecules formed from the raw ingredients of Pluto's atmosphere. On Titan, Saturn's largest moon, a similar haze warms the surface, trapping heat like a blanket. But on Pluto, this haze does the opposite, creating a chilling effect. Recent observations from the James Webb Space Telescope, or JWST, revealed that Pluto's haze particles are perfectly sized, almost as if by design, to efficiently absorb incoming sunlight and then re-emit that energy as infrared radiation, effectively cooling the atmosphere. Imagine a black car sitting in the sun on a hot day. It heats up dramatically, absorbing the sun's energy and radiating heat. But now imagine spraying a fine mist of water over that car. The evaporation of the water cools it down by carrying heat away into the air. Pluto's haze acts like that mist, but instead of water, it uses infrared light to shed heat. This process intercepts solar energy high in the atmosphere, far above the surface, and then jettisons that energy directly into space before it has a chance to warm the surface of the dwarf planet. The confirmation of this anti-greenhouse effect is not just a small step, but a rare scientific triumph, a moment of true understanding. It validates bold theories about planetary atmospheres, and vividly shows how a planet's climate is a delicate balance of chemistry, pressure, distance from its star, and the properties of its atmosphere. Change just one variable, even slightly, and you can get a completely different outcome, a world transformed. Pluto's haze is more than just a pretty feature. It's the central cog in a bizarre, unexpected, and wonderful climate machine, a testament to the diversity of planetary processes in our solar system. JWST's surprises didn't end with Pluto. Charon, its giant moon, had secrets too. Charon, once thought to be a simple icy satellite, revealed a complex surface chemistry. JWST detected frozen carbon dioxide, primordial material exposed by ancient impacts. But the real shock was hydrogen peroxide, a highly reactive compound formed when radiation bombards Charon's water ice. This means Charon's surface is actively altered by space radiation, not static as once believed. These discoveries transform our view of Charon from passive satellite to dynamic world. Its surface chemistry is evolving, shaped by both ancient and ongoing processes. Together with water ice and ammonia, these findings offer a complete chemical inventory of a Kuiper Belt object. Charon's story is rich and active, providing crucial clues to the solar system's formation. The Pluto-Charon system is more dynamic than we ever imagined. Pluto and Charon are two chapters of the same cosmic story. Their binary system is a laboratory for planetary interactions. Pluto's atmosphere escapes into space, some of it lands on Charon, painting its poles red with tholins. Charon's surface, meanwhile, is reshaped by radiation chemistry, forming hydrogen peroxide and exposing ancient ices. The interplay is complex. Pluto's haze and escaping gases interact with Charon's evolving surface. Do Pluto's complex organics reach Charon? How do they mix with hydrogen peroxide and CO2 ice? The system is a dynamic chemical experiment spanning thousands of kilometers. Studying Charon's surface reveals Pluto's atmospheric history. Understanding Pluto's climate predicts what lands on Charon. JWST's dual observations let us study this interaction in unprecedented detail. The Pluto-Charon system is a unique window into the evolution of binary worlds. Pluto's strange climate has implications far beyond its orbit. It forces us to rethink other cold, hazy worlds, like Neptune's Triton and Saturn's Titan. Could Triton's mysterious energy balance be explained by a similar haze-driven cooling? JWST's discovery on Pluto provides a new hypothesis for these distant moons. Even Titan, with its thick, warming haze, might have upper layers where cooling dominates. Pluto's climate engine adds a new variable to our models, refining our understanding of hazy worlds. This insight is crucial for studying exoplanets, distant worlds with unknown atmospheres. We can no longer assume haze means warming. Pluto proves it can mean cooling. As we interpret future data from JWST and other telescopes, Pluto's lesson will guide us. The universe has more ways to regulate a planet's temperature than we ever dreamed. Pluto's discovery expands our cosmic climate toolkit. Pluto's revelations may seem remote, but they echo back to Earth. Its haze offers a glimpse into the chemistry of early Earth, before life began. Ancient Earth may have been shrouded in a similar haze, influencing climate and the origins of life. Did such hazes warm or cool our planet? Pluto's anti-greenhouse effect provides a real-world test case. Studying Pluto's atmosphere helps us understand how complex organics form, key to life's building blocks. The discovery of a new climate mechanism is a humbling warning. Planetary climates are fragile and complex. As we alter Earth's atmosphere, Pluto reminds us that nature's climate systems can behave in unexpected ways. Even the smallest, most distant worlds can hold revolutionary secrets. Pluto's cooling haze and Charon's reactive chemistry open new research frontiers. The demoted planet has given us a promotion in cosmic understanding.